All right, good morning, everybody. Welcome to reInvent. Welcome to NET402. Yeah, let's get excited. Welcome to NET402, an ambitious crew here getting into a 400-level talk first thing Monday morning. My name is John Pangle. I'm a senior product manager in EC2. I focus on instance networking, and I'm here with my colleague, Scott Wayner.
Welcome, everyone. Scott Wayner, I'm a principal solutions architect, and I'm working very closely with John on a lot of the work that I'm doing with my customers on accelerating and getting high-performance throughput for Nitro. So hopefully you're here because you've had situations like that check engine light comes on in your car, and you're like, open up the hood, and you look like, what's going on? I have no clue. Or you're waiting to get tickets at a venue, and the line doesn't seem to be moving, and you're looking for that, what is going on? How do I get my tickets quicker, or the seats that I want? So what we're going to do today is dive into Nitro and help you through those processes. Now, we can ask, why are you here? So as a show of hand, how many people are from like an engineering capacity, like planning? We got a great number of people here. How about operations? Any folks from operations? We got a handful. We're going to help you guys out too. How about application developers? We got a handful there. So hopefully all of you are going to have something you can take away out of this. And the reason is that we're going to walk through an entire sequence of services going down into Nitro so you can take advantage of what we're doing with Nitro. So with that, I'll hand it over to John.
Yeah, so you might be asking, why are we here? Product manager, solutions architect. As Scott said, his job is focused on optimizing and improving customer workload performance. My job is focused on building and delivering new products and innovations in the networking space from an instance networking perspective in the data plane to continually evolve our data plane and improve our network performance and our network connectivity. Today, we're going to walk you through some of the deep dive into Nitro from a VPC networking perspective, because those two things, our data plane and our VPC networks, are deeply connected. This data plane powers millions of servers, billions, if not hundreds of billions of packets per second. It runs all of the applications you know and love, from the Amazon store, of course, to Netflix, to everybody here's workloads, right? Like this, the EC2 data plane is very, very intricate, but it is very, for some of our customers, it can be a black box. We want to walk you through some of the tricks and tips to understand how that data plane works so you can better optimize your workloads. So a quick overview of our agenda today. We're going to take you through a packet analysis to understand how a single packet flows through an EC2 instance. While the network supports billions of packets per second, every single packet matters, and understanding how one packet flows is critical. From a single packet, we'll take you to a single flow to understand how a flow is optimized once a connection is established. From there, we'll go into a multi-flow analysis to talk about how an instance works with many flows. And then from there, we'll give you some additional tools and tricks to help you understand how to optimize beyond that from a latency and CPU perspective. And finally, we'll give you an action plan to take away. But first, we want to talk about what Nitro is. It's an umbrella term. It covers a lot of things. Nitro is a system of chips that represent our networking, our storage, our block storage, our local storage, security, and so many other things that power so many of the capabilities you know and love. When we first came up with the idea of Nitro in the early 2010s, we saw an emerging trend. Our server density was continually increasing generation over generation. We were able to fit more instances onto a host CPU, but the proportion of the networking I/O, the storage I/O, and the security capabilities were becoming bigger and bigger as customers like yourselves demanded more capabilities from our EC2 instances. And it became harder to plan and provision how your application would work with your networking and your storage. And therefore, in 2013, we took the radical decision of off-boxing our capabilities with enhanced networking with the C3 instance, such that we started moving our processes off of Nitro, or off of a server onto Nitro chips, such that we would off-box networking, storage, and security, and all that was left on the host was a lightweight hypervisor. We didn't stop there, so we first took a step with C3, but then we've since launched multiple generations of Nitro in partnership with our Annapurna. And to date, we have launched 5 generations of Nitro. First starting with C4, and then all the way up to Nitro V5, C7, GN, and there's more to come, of course. But as you can see here, with each generation of Nitro, we're continuing increasing the performance bar from a bandwidth perspective, a packet rate perspective, but also from a security perspective, as we're adding encryption, as we've added encryption in transit for all Nitro capabilities since Nitro V3. So again, I want to give you a quick overview of what we're going to cover today so you know what you're in for. First, we're going to talk about a packet analysis, how a single packet flows through EC2. From there, we're going to go into a flow analysis. So once that connection is established, what does a flow look like? And then from there, we'll talk about multiple flows. And for that, I'm going to hand it off to Scott to start with the packet analysis.
Thanks, John. So in this segment, we're talking about a single packet and as it works its way down through your application, through the kernel, into the drivers and into Nitro and then out of the host. And to that, we're going to focus on this processing stack. Then we're going to show you how the VPC is encapsulated as represented in Nitro. Then we'll look at the packet processing within Nitro, and then we'll look at the Nitro state machine. So let's step right into that process. Now, throughout this presentation, we're going to use this representation of the stack, the application, the kernel, the drivers, Nitro, and then, of course, the Ethernet that's actually moving the packets between compute hosts. You'll see there's a dividing line. Everything above the dividing line, that is your instances, that's your CPUs that we're not touching. We give you the drivers to interface with Nitro. Nitro is a Nitro card that sits underneath the host. And therefore, there's a clear demarcation, and the drivers that we present as part of the Nitro is where you'll use this. Now, this representation stack, we're going to keep it up in the top right corner of the slides throughout this, and we'll highlight the section of the areas that we're talking about as we take a packet and move it down the stack from your host all the way into the Nitro card and out. So let's start with the VPC construct to give you a kind of an overview and a frame of reference for our conversation this afternoon or this morning. So what we're going to do is have a client. We're going to be talking in through an internet gateway, and then you have your VPC. Now this is a typical type of VPC interaction where you'll have some form of gateway. In this particular case, I'm showing a gateway with two interfaces. This could be a firewall, it could be a router, it could be some kind of proxy type instance, but it's your external subnet. Then we're going to have an interaction from that into our web server. This is the front part of a three-tier architecture that you might be using as a reference. From the web server, then we'll be talking to an app server behind it. This could be on your business logic layer, using the elastic network interfaces, and finally to a database system. There's many different ways of dealing with this. However, we just want to use this as a frame of reference so you can have an idea of what we're talking about when we go into the specific elements of the processing of Nitro. And for that, for the next section, we're just going to focus on this specific piece between the web server and the app server. In particular, the packets that are leaving the web server and going to this app server and back. So we start with the packet processing. We're going to take a packet, which is represented here as an IP destination, IP source, protocol, destination port, and source port. And we're going to use that as our reference going throughout. And this is critically important that you understand how Nitro works with our systems. So we start out with our packet that we're creating. And so from our web server, we're just basically hitting an API. We'll just use a curl as an example. Over to our app server, we're going to get a file. We can do a DNS resolution. That'll give us a destination IP address. Now, the application itself is basically pointing to the port, like port 80 or port 443 or something like that, and then we're going to get the data. But what we're going to be doing is we're going to open up a TCP socket. Now this is all in your kernel operating layer into the device drivers. This is going to give you a 5-tuple. I want you to remember the 5-tuple because this is going to be very important as we start to process this packet down in Nitro. And again, source IP, destination IP, protocol, source port, and destination port. That is your 5-tuple. Now, once we have this packet, we're going to make a routing decision out of the operating system to a specific device. In this case, it might be ENS5 as a representation. Now that is going to be mapped to an elastic network interface. The elastic network interface is actually in Nitro. And this is all part of the elastic network adapter. So you can see that the Nitro card has your representation of elastic network interface, which is then associated with your device in your kernel operating system. From there, we're going to take that destination packet, and now we're going to figure out how we build the state machine within Nitro. Now you see that packet's going to be leaving the operating system and coming into our elastic network interface, and you can see that depicted on the right. The first thing that we have to do is we have to figure out which queue that packet's going to go in. And you'll see that we have a set of queues for this elastic network interface for transmit, and we have a set of queues for receive. Associated with that set of transmit queues, there's a ring. That transmit ring and receive ring is where we're going to be putting packets onto the ring and handing them off to your operating system. And then below that is the network interface, where we'll take the packet and send it over to another compute instance. Now, an important point is that we're going to be hashing on that 5-tuple. That 5-tuple hash is going to do the queue assignment and the processor associated with it in Nitro. So that 5-tuple is going to come back to be very important for you, is understanding how you're going to be handling packets into those queues. Now, once we get the packet, we're in Nitro, and now we have this representation of a VPC. The VPC is represented inside the Nitro card. That is your subnets, etc. Now, once we get to that packet, we have to start doing some things that are going to be the first time we've seen this packet. And the first thing we're going to do is we're going to look at the route table that's associated with your subnet, also in Nitro. That route table might say, hey, we're just going to do a local route in this particular case because we're only going to the app server that's adjacent. The second thing that we have to consider is the network access control list associated with the subnet. Again, it's a configured state in Nitro. And then finally, we have the security group, which is defining whether we're going to allow this packet out or where we're going to allow this packet in. Now, that Nitro configuration is going to be used. Now, you're configuring the Nitro state, either through the console or APIs, etc. However, this is the first time we've seen this packet, and therefore, we're going to build some Nitro state. In order to do that, we need to figure out where to send this packet to somewhere else in this VPC construct, which is another Nitro card somewhere in the network. To do that, we're going to do a lookup on that IP address. And with that, we're going to use a mapping service, and we can basically look up for that destination IP address, where in this network of other Nitro cards do I need to forward this packet to? Once I get that answer back, I can build an adjacency in Nitro, and I can remember that state. And this is going to be important as we get to the latter part when we talk about multi-flow. Now, you also have something that is a connection tracking mechanism. And in this particular case, we've only seen the packet one way at this point. And this is going to be referred to as a contract, which is basically saying, hey, there's a relationship between the web server and the app server, and I want to keep track of that state. And then finally, we're going to build a flow cache. Flow cache is going to be one of those mechanisms that we can accelerate the packet through Nitro. And so our goal here is to build that Nitro state. Now, the first packet that's coming through, we're going to be in processing path. We've never seen this before. We're going to do all this state setup for the first packet that's originating. And you're going to see lower packets per second at that point in time because we've got to do all the processing. Now, the packet leaves our web server, goes over to our app server does its thing, and then basically we'll have a chance to send a response back to us. Once we get the response back, you'll see that now we've seen the reciprocal packet come into our Nitro card. In this particular case, the connection tracking is now established. We have an established connection. You'll also see that the flow cache is complete. So now we can accelerate all the remaining packets for this transaction. This is what we would call an accelerated flow. Now that packet's going to come back up through Nitro. It's going to be placed on the receive ring, aligned with one of the receive queues, and then handed off through the Elastic Network Interface into the drivers of your operating system. Now we'll have a 5-tuple hash on the receive side, which is going to assign it to a receive queue. And therefore, you're going to see these packets arrive on the receive queue. Now, take note of where these packets are arriving because there's different ways of we'll receive those packets on those queues, and John's going to give you some more details later about how we can do that. So with that, I'm going to hand it back over to John for that flow, since we have now completed one transaction.
Yes, now that we have a transaction completed, we've entered the accelerated path. This is a critical capability and thing to understand. When you're in the accelerated path, less work is required from Nitro, and therefore your capabilities, your system performance goes up. So once you're in the accelerated path, though, you need to understand what a single flow spec or instance is capable of within a single flow. From there, we're going to touch on some common challenges that customers run into. One of the biggest ones that we hear from all the time is around microbursting, so we'll give you some tips and tools to understand how to manage that. We'll talk about some anomalies with flow state that can break a connection or have an impact that you need to be aware of. And then finally, we'll talk about whale flows. While whale flow can be common with TCP or UDP, there's some other edge cases that can arise where whale flows need to be considered in more detail. So first we want to talk about a single flow specification. By default, the vast majority of flows on an EC2 instance, traversing an EC2 instance, are capable of achieving up to 5 gigabits per second. This is a flow from the external internet into an EC2 instance and vice versa. This is between any two AZs or between two regions as well. You can also be subject to a 5 gigabit capability within your availability zone. We set this limit at 5 gigabits in order to provide a consistent experience for you, but then also to protect our infrastructure so that you can avoid networking congestion and hotspots such that you get a consistent performant experience from day to day. Beyond an external flow, or a default flow, we have what's called the cluster placement group flow, which allows up to 10 gigabits per second with TCP and 8 gigabits per second with UDP. A cluster placement group is a launch mechanism for your EC2 instance, and it's physically co-located your two EC2 instances close together such that you can achieve up to 10 gigabits per second. And then beyond that, we have a recently launched capability called ENA Express. ENA Express is an enhancement to ENA that uses an SRD, or advanced congestion control algorithm, that allows up to 25 gigabits per second for a single flow. Now, unlike an external flow, which works everywhere, or a cluster placement group, which works based on a launch configuration where you physically launch your EC2 instances, ENA Express is a instance level capability that needs to be configured when you launch or modify an EC2 instance. So now we want to take a look at this in theory. What does this actually look like? So here we have a cluster placement group flow on this green line, and we have an external flow, or a 5 gigabit flow, this yellow line. This graph represents your packet size on the x-axis and your actual bandwidth on their y-axis. So as you can see, with a small packet size in the 64, 128, et cetera byte range, you actually end up being packets per second constrained. Eventually, as your packet size gets larger, you become bits per second constrained. And this is dependent on not only your Nitro capabilities, your Nitro processor generation, but also your EC2 instance specifications. As you can see here, both follow a similar trend line such that your packets per second constrained up to a point where you then become bits per second constrained. This is an important consideration to understand how a single flow operates, not only from the bits per second or the single flow bandwidth perspective, but also the packets per second capabilities. So that's in theory. Let's take a look at this in practice. We launched and ran a C5 large and a C7i large. These are Nitro v3 and Nitro v4, Nitro v2 and Nitro v4. So multiple generations of improvements here. But as you can see, with the I lose the colors here. The pink lines and the red line, which represents the C7i, we're able to achieve the performance a little bit sooner on the packets per second capability as opposed to the C5 large, which has a newer Nitro generation, older Nitro generation. But both follow that similar theoretical trend line that we depicted earlier, where you're at first packets per second constrained before you eventually become bits per second constrained as your packet size increases. All right, let's talk about microbursting. Has anybody ever had a challenge with microburst before? Folks know what it is? Do you know how to diagnose it? It can be very challenging to diagnose, especially on an EC2 instance if you don't understand when and how it can happen. So what causes it? We'll dive into that very briefly, and then we'll give you some tricks to prevent it and to manage with it. But first, before we talk about a microburst, we want to talk about what an actual network burst is. So here we have another graph. We have a time scale on the x-axis, throughput on the y-axis. What you can see is that within a narrow window, so within approximately 6 seconds, we're pushing 10 gigabits per second for each one of those seconds. Now what this looks like in reality is exactly what is depicted here, where you'll have a spike in your throughput and then it'll come back down. But if you're using your ENA metrics, or your instance metrics via CloudWatch, what you'll actually see is 1 gigabit per second over a 60-second timeline via the enhanced metrics. Essentially what you're getting is an averaging effect that smooths out your throughput. And so you might look at your metrics and say, hey, I only actually pushed a single gigabit over this minute, but in reality what you were doing was pushing 10 gigabits within 6 seconds, and then that metric was averaged out. So again, we want to test this and prove it in theory. So again, we did iPerf test, C7i large, transmit to receive, and then we took the output of those, pushed it to CloudWatch, and we did some metric math to convert it from bits per second to megabytes per second. So here we have a test. We ran it for 6 seconds. We used a packet size of 9,000 bytes, and we had a single stream. And as you can see on the output, for each one of those 6 seconds, we have roughly 9.5 gigabits. And for the course of those 6 seconds, we have here 9.5 gigabits as well. So over that 6 seconds, we have exactly 9.5 gigabits per second. Now, we take that, we do our metric math in CloudWatch, and what this comes out to is less than a gigabit per second on an average. Therefore, you have this very nuance of like understanding that is critical to understand how a network burst occurs before we go into how a microburst occurs. Now we can do the same thing. In this case, we actually did a similar test, but we did 8 flows, each flow targeting 10 gigabits per second, each flow using 9,000 byte packets, and we were using UDP in this case so that you're not going to have your TCP overhead, which is going to do your backoffs and congestion management. In this case, what you'll see here is that each one of those flows is actually rate limited down to approximately 3 gigabits per second for a cumulative egress throughput of 26 gigabits per second. But this is a C7i large instance. A C7i large instance is capable of doing up to 10 gigabits per second. So in this case, trying to push 26 gigs on a 10 gig instance is not going to work, and you're going to get packet drops. So this is a very real problem that can and does occur. So what actually causes it? In this case, what is happening is that your packets are arriving faster than they can be processed on Nitro. As a result, what will happen is our queues that we talked about briefly, that Scott talked about briefly, will back up. Eventually, those queues will fill up, and you'll get delays, but then eventually drops. And our metrics will index accordingly. So there's mechanisms to prevent this. We have congestion controls that you can use within the queues and within the kernel that will allow you to manage microbursts more effectively, such that your actual packet drops do not, or such that you don't actually achieve packet drops, and you're able to optimize and have a consistent network performance. So in general, some of the things you can do is increase your RX queue depth, such that you have a bigger buffer for more packets to hold in memory. Of course, there's a downside. The more packets you hold in memory, there's a chance of latency, latency increase, excuse me. In general, on TX, or on the transmit side, you can use traffic control, which is a Linux kernel capability which, with queue disk and fair queuing, which allows you to rate limit your total system throughput as well as individual flow or queue throughput. And then finally, I mentioned it earlier, but with Nitro v4, we have a capability called ENA Express that manages incast scenarios or ingress microbursts very effectively via congestion control algorithm. All right, so let's take a look here. We have a C6i instance, an 8x large with 16 CPUs. By default, the majority of our instances support up to the number of CPUs as queues, and then on some of our accelerated instances, our network enhanced instances, we support up to 32 queues. By default, on our latest generation of Nitro drivers, we support a TX ring depth of 512. This is with a capability called wide LLQ. And on the RX side, we have a default of 1,024. Now, in either case, what you can do is actually increase your queue depth, or your ring depth, such that you can hold more packets. But on the TX side, you'd actually have to disable wide LLQ. And this is primarily a capability that allows you to have more descriptors or more options within your header. So if you're using IPv4, you don't have a lot of descriptors, you can disable wide LLQ. But if you're using IPv6, you're adding a bunch of descriptors, you'll want to enable wide LLQ, and then you'll actually be limited to 512, or 512, excuse me, on your TX ring depth. But when you increase this on the RX side, what you'll actually be able to do is hold more of those queues in memory. Now, traffic control. This is a capability on the transmit side that allows you to rate limit how many packets you're actually pushing from the kernel down to the networking stack. So in this case, we ran an iPerf test for 10 seconds with 10 streams, and we just allowed it to run. In this case, it actually tried to push 10 gigabits per second on each one of those, for each one of those seconds, and for a total of 93 gigabits per second. Again, this is a C7i large. Like I said before, it can't do 26 gigs. It definitely can't do 93 gigs. So something's going to go wrong here. You're going to have flooding, microbursting, or packet drops. Now what you can do is enable traffic control, set up classes of traffic, and then enable fair queuing such that you can rate limit your entire system with a token bucket and 10 traffic classes. But you would set your max throughput to be approximately 10 gigs in this case because that is our instance spec limitation. And then you would actually set your individual instance or flow limit or queue limit to a single gigabit per second. In this case, what it'll do, or what this will enable you to do, is rate limit your entire system so that your kernel won't actually push more than 10 gigabits across the board, but also won't try to push more than a single gig within a single flow. And just again, real quick, wanted to demonstrate this in practice. We essentially ran the same test just after the kernel configuration. As you can see here, each stream is approximately 964 megabits, or just under a gigabit per second, and our total system throughput is under 10 gigabits per second, or 9.6 gigabits per second. And then the last capability here that I want to talk about, of course there's many others that can help you manage microbursting, but I just want to touch on a few, is ENA Express. So a quick overview of ENA Express. It was launched in 2022, and again, it enables 25 gigabits per second of flow throughput. It has built-in congestion control based on SRD. So if folks are familiar with EFA or the Elastic Fabric Adapter, which powers our machine learning and AI applications, SRD is that protocol inside of Nitro that actually does congestion control on the Nitro card. We took that capability for EFA and for ML and HPC applications and ported it over to TCP and UDP-based applications such that we get that congestion control for regular applications. And this allows you to react well to an incast scenario or an RX microburst, but it also helps with your P99 and plus tail latencies as it does the congestion control directly within Nitro at a lower layer in the stack in the Nitro firmware as opposed to up in the kernel. And again, this is supported on Nitro v4 and later instances, and it is a customer opt-in capability, and it's available within a local zone. And if we haven't said it before, we do have some nuggets here in the bottom right throughout this presentation. We will be referencing these again at the end, so please feel free to take them now, but also they'll be available again later. All right, now we want to talk about a couple flow state anomalies. So there's a couple things here. First, a VPC mutation. So as Scott walked you through, a single connection is established based on your state. So again, we have a web server and we have a Nitro state machine or a Nitro configuration where you have your routing table, your ACL list, and your security group. ACLs are stateless, so that they only allow traffic in based on a single direction. They do not allow traffic to return. So if your ACL is updated, you change an ACL list, you want that Nitro, or you want your EC2 instance to respect that. And therefore, if you're actually going from a more restrictive or a less restrictive to a more restrictive ACL, you could potentially break that connection. Now, if you're going from less restrictive to, or excuse me, more restrictive to less restrictive, you'll still have to reevaluate that packet and the processing path, but you won't actually break that connection. Similarly with security groups, or not similarly, dissimilarly with security groups, they are stateful, which means that a packet coming in is allowed to egress out, and vice versa, depending on your actual first packet that is received. In this case, we have a security group that allows any source IP address for protocol TCP to a specific port range of 443. Now, if you go from an open or on-track security group to a track security group, we will actually then enforce that security group and we will reprocess that packet. But if you do the opposite here, where you go from a closed security group to a more open security group, we won't break that state and we'll continue to operate it as a stateful connection in this case. But I touched on something there that was really important. On-track connections. So here we have a security group configuration for your inbound and your outbound rules. We have multiple TCP protocols in here. In this case, we have port 80. So we have a HTTP port 80 for 0.0/0 and 0:0/0 for IPv6. And in this case, all IP addresses are supported on the ingress side, and all IP addresses are supported on the outbound side. On the flip side, with port 22 for your SSH capabilities, we have a specific source IP address that we're allowing traffic in because we only want to allow traffic in from our actual development environment. In that case, that is a track connection, whereas the port 80 is an on-track connection. And then there are some things like ICMP that are always tracked. Now, on-track connections are a super important thing to understand because they will allow for your application to perform better because you don't actually have to evaluate the security groups. Now, there's a trade-off there, of course, right? Security groups are important and they're a critical application. But in there's certain circumstances, if you're running, say, a network appliance like Scott depicted at the front end of your three-tier architecture, an open or an on-track connection allows you to push your processing into your actual firewall that might be operating on the EC2 host. And it's a bit like opening up the floodgates of a dam. You're basically allowing Nitro to do as much work as possible so you can push your work up the stack into your host CPU and into your business logic. And then finally, in this section, I do want to touch on a minimum driver requirement. So as you go from Nitro v3 to Nitro v4, there's a minimum ENA driver version that is necessary in order to take advantage of the accelerated path. On Nitro v5, this is actually required, whereas on Nitro v4 it is recommended. But the latest, that version of the driver, and there's a few versions since then, but starting with 2.2.9, there is capabilities built in to allow for you to actually take advantage of the hardware acceleration capabilities we built into Nitro over time. And if you don't use that, you'll actually be continuously operating in the processing path, which can impact your overall system performance. And last, moving on to the whale flows in this flow analysis section. So a traditional flow, TCP UDP flow, will come into Nitro. It'll hit the queue. It'll hit the Nitro card. But you'll notice something different in this case. We have a source and IP destination, an IP tunnel, and we have an inner IP packet and an inner IP payload. So you have one packet. We have this blue packet here, and then we have another packet, this pink packet here. As you can see, something is different. In this case, we still have two different unique IP addresses or IP payloads within this tunnel, but they share the same common 3-tuple. So Scott made a really critical point earlier that it is important to understand and evaluate your flows based on a 5-tuple. In this case, when you have a generic IP packet, we're actually evaluating on a 3-tuple flow. So even though you have unique packets here, blue packet and pink packet, or purple packet, you're actually going to have the same generic 3-tuple, and they're going to be treated the same on the queue and on your Nitro processing. So again, unique 5-tuple packet inside of your payload, but your outer IP tunnel protocol here, such as GRE or IPsec, treats this, results in Nitro and our ENA queues treating this as a 3-tuple. So that in this case, they are actually represented as a single flow. So all these single flow considerations we've talked about are applicable to a GRE tunnel or an IPsec tunnel or any other generic IP protocol like an IP and IP that will look like a 3-tuple flow. Now, how do you break out of this? Well, you still have your unique 5-packet or 5-tuple packets inside of your tunnels. But what you can do is use a UDP-based encapsulation protocol. So VXLAN is a very common one on-prem to extend your data center. There's Geneve, which is a common protocol that's recently developed that is still trying to gain some traction. And there's GDP, which is commonly used in the telco space. And there's also like MPLS over UDP. So depending on your application, where you're actually operating, you can use a different UDP-based protocol to create entropy such that each one of these flows will actually be treated differently inside of Nitro and inside of our queues to improve your overall performance such that they're treated as individual single flows. So now in this case, we have a UDP header with a unique tunnel. So each one of these is treated as a unique 5-tuple. And ultimately, they're hashed differently on Nitro, but also hashed differently to queues, allowing you to distribute your load more evenly. And with that, we're going to conclude the single flow as I naturally transition from a single flow to breaking that into multiple flows and hand it off to Scott to talk about multi-flow analysis.
Thanks, John. So it's critical there you see that anytime you're doing a tunneling mechanism, you understand what's happening in the tunnel, because what we're going to see in those cases is where those GRE packets or IPsec tunnel packets are going to be treated as a single flow. And they're going to be processed in the Nitro and sent to a specific queue. And so you're going to be dealing with that specific queue. And John's going to show you a little bit later in how we'll deal with multiple flows in the queues and the processors that are in your instance. So let's take a look at that number of flows. Now, what we've talked about is, let me back up one sec. Number of flows, the burst bandwidth, and baseline bandwidth, those attributes are specified. You can go look those up, and we'll have those in the QR codes at the end. Below the line, packets per second and shared Nitro resources are basically mechanisms that we're using to try to ensure that you're getting the quality service that you need throughout. However, there's so many variables in there. Our recommendation is that you test to make sure that your application is going to get the packets per second and the resources from Nitro that you need. So we'll start with those number of flows. As John kind of highlighted, we have in this depiction here, we have a couple of tunnel flows here, and what we've got is a 5-tuple, and with that 5-tuple, they're unique. When we hash them, we can assign them to different receive and transmit queues. That gives us that horizontal scale where we can spread those loads across multiple queues, and as we hand it off to your CPUs in your instance, multiple CPUs on your side. So this is unique in the fact that we're going to use these flow hashes, and we'll have independent queue assignment of these different mechanisms. There is a notion of flow symmetry. It's not critical, but just so you know, when you use your ENA enhanced metrics, is that some of the older Nitro cards like V3, they use independent assignment of the queues. So what you're sending of a particular flow might go out on Q0 and come back on Q4, whereas Nitro V4 and beyond, we've gone back to a symmetric, so the metrics kind of line up, but just be aware of that. So let's take a look at burst bandwidth. Now again, we're talking about multiple flows here. So this is at the instance level. What does the burst bandwidth mean? So I've given you a hypothetical situation here where I've got a C7i instance. The burst specification is 12.5 gigabits per second. The baseline is 780 megabits per second. And if I were to map those out, you can see that those are the limits that we're going to be invoked for this particular instance. And if I take a hypothetical transmission from like my web server to my app server, you can see that I'm going to start transmitting, and I'm starting at 0 in this particular case. Now, when you boot up your instance, you're going to get a set of credits for bursting. In addition, as long as your traffic is below the baseline, you accumulate credits. And you can use those credits. As you burst above the baseline, you start consuming those credits, and we allow you to continue to burst until all your credits are consumed. And note that we can go all the way up to that burst bandwidth. Now, the question is, how long are you going to stay in the burst mode? But once we've consumed all of those credits, now we're going to put you back down in the baseline. Now, this is critical for your design choices here. Is if you know that your application is aperiodic in its workload requirements, then you can take advantage of burst properties to actually get smaller instances, burst for a short period of time, and then move on. But if you have a sustained workload that's going to be constantly processing traffic, you need to pay attention to the baseline to make sure that you're able to sustain that load. So what we did is we said, okay, let's take a look at this burst bandwidth capability. Now, it's the sum of the ingress or the sum of the egress. Those are two separate metrics that we're going to be monitoring. We're going to look at the burst credit availability. Now, note that we're going to be focused on the burst, which is 12.5 gigabits per second. I'm going to transmit from the transmitter to the receiver, large MTUs. I'm going to try to hit the burst limit, and then you'll see that I'm rate limited to the instance specification. So we set up a test. In this particular case, I've got a 1-second burst. It's a 9,000 byte packet. I'm doing one stream. And what you'll see is that I'm now constrained to that instance capabilities of the cluster flow. Now, this is the cluster flow limit, right? However, if I get 2 streams, in this particular case, I've still got, the 9,000 byte limit, 1 second. But what you'll also note here is I'm able to get all the way up to the burst limit because now I've got 2 streams. This is multi-flow. And I'm able to get, beyond that cluster placement group limit of 10 gigabits per second. Note that the 2 flows are going to be roughly evenly balanced. And so I get an instance aggregate all the way up to the burst specification of that instance. This is public. You can actually monitor it with your enhanced network metrics. These are your bandwidth allowance in and bandwidth allowance out. Now, we've spent a lot of time talking about the baseline. Let's take a look, or the burst, let's take a look at the baseline bandwidth. Again, baseline is the sum of the ingress or the sum of the egress. So let's take a look at what happens when we do a multi-flow test for the baseline capabilities. Now, note that we're going to use this test for a time period to make sure that we've consumed all of the credits. And then once we hit those, or credits exhaustion, then we'll have our traffic constrained to the baseline. So here you can see that I'm running this test for 600 seconds. And I'm using large frames, 9,000 bytes. And I'm going to be doing 2 streams. And you'll note that I'm now basically constrained at the baseline capacity. So I'm running this low workload for a long duration of time, but I can sustain that baseline capacity for the duration. And that's the instance aggregate baseline flow limit. And you'll note that the 2 streams are basically getting roughly the equal share of the capabilities. Now, this particular test was executed immediately after I had consumed all of the credits. So that's why you'll see that baseline. If I stop the test and then restart it, 5 minutes later, I've already, reestablished some credits. What this looks like in aggregate when we look at our baseline and our burst capabilities is we've run this test for a duration of time, and you'll see in CloudWatch I've captured the data over an extended period of time. The first part you can see here is I'm consuming my credits. I have a set of credits that I have accumulated, and I'm consuming those credits. Then I hit my burst limit, right? And I'm going to be at that burst limit of that instance. That's a specification. We'll give you the links to get that. Finally, I've exhausted all my credits. The traffic starts coming back down, and now I'm going to be sitting at my baseline. And my baseline is going to say, here's where you can get your continued throughput for the duration, and then finally I end the test. Now we'll go into packets per second. In our packets per second, again, the sum of ingress, the sum of egress. We'll do a similar test, but note in this particular case, we're going to use a small MTU. In this case, we're going to do 128 byte packets. And we're looking at instance limits and flow limits, et cetera, and these are aggregated across the queues. So in this particular case, I've got one flow, one queue, and I'm doing 128 byte packets. My duration is 10 seconds. And you can see that I'm going to hit a target packets per second for this instance of roughly about 928 megabits per second. And I'm basically hitting the limits of the packets per second. In this case, it's about 1,000 kilopackets per second. Now, if I end up doing a second test with 2 queues and 10 seconds, I'm still going to get my capacity there of 928 megabits per second. Now I'm at the instance aggregate flow limit, again, 972,000 packets per second. So I'm basically hitting that limit of the packets per second of the instance. Now again, it's a target, it's not a commitment. And what you need to understand is, how quickly can you get traffic into accelerated paths? How many connections are you setting up? How frequently you're changing those attributes? But this is what it looks like, is the instance is packets per second bound on the smaller packets up until we get to the full-size packets of roughly 1,000, and then we start to hit the bits per second. Now, the 2 flows are now constrained within that profile, roughly equal. So this gives you the idea of what's happening with our packets per second. Again, these are available in your enhanced metrics. You can get this value from your drivers, which is your PPS allowance exceeded. You'll take a look at that and you can extract that information. And finally, shared Nitro resources. Now, one of the principles that we have is that in this particular case, we've got a host with 64 cores, and you happen to instantiate an instance with 16 cores. You get your ENI, you get your receive and transmit queues, you get your rings. And basically, Nitro has a cycle time. Here's all the time in the world that we have to process packets. Since you've got roughly 25% of the cores, we should at least make sure that you're protected with 25% of the cycle time on Nitro. However, we don't hold you to that. We allow you to take advantage of extra Nitro processing cycles as long as there's time available in that cycle path. Now, again, packets per second allowance exceeded. This allows you to maximize and get accelerated flows. You can use larger packets. You can use long-lived flows. And that way you can maximize your time on the Nitro from a cycle time. Now, what happens if somebody else happens to land on the same host? Now, in this particular case, it too is going to get its protected resources. And so we're going to allow them to have their time on the Nitro cycle time, but they too can burst. And so this extra cycle time in Nitro, everybody can take advantage of it opportunistically. But from a shared tenancy perspective, we're doing resource isolation, we're doing contention mitigation, and we're trying to maximize the throughput for you and your neighbor. Again, these metrics are available with the PPS allowance exceeded. And with that, I'll hand it back over to John for some of these tuning and monitoring tools.
Awesome. Thanks, Scott. So we've walked through a single connection, a single flow, and multiple flows. Now you have your instance set up, you have your 3-tier architecture set up, but it's important to understand how to manage beyond that, right? So there's other considerations. Latency is one of those. And what I should have put directly parallel to this is CPU management on your host. These things are intricately related, but they also have a relationship with queue management. And then ultimately, we're going to touch on some additional monitoring tools in a little bit more detail. So first, when it comes to latency, there's nothing you can do to overcome the laws of physics and the speed of light. Therefore, using cluster placement groups, or CPGs, is a capability that allows you to co-locate your instances as close together as possible, such that you're going to reduce the distance between your instances and have the lowest possible latency. Other capabilities within the application stack include driver capabilities. So DBDK, or the Data Plane Development Kit, bypasses the host kernel and allows you to do packet processing in user space, such that you can reduce some of the overhead or your latency from the kernel and improve your latency in that regard. Or you can use protocols like UDP as opposed to TCP, which reduces some of the overhead from the TCP stack. So if we move to the kernel, there's also a capability called pull mode operation. With pull mode operation, effectively what this host CPU is doing is continuously pulling packets off of your queues in a tight loop, such that as packets are received, they're pulled and processed in the host CPU. Or you can use higher C states. The deeper your C state, so something like a C6, is a lower power consumption, but it's going to require additional time and therefore latency delays to move from a C6 state to a C5 all the way up the stack. If you configure your host CPUs to be in C0, you'll be at the lowest possible latency, but you're ultimately trading in that off for power. So all of these considerations, a lot of these considerations come down to power versus, or a host CPU utilization versus a latency trade-off. Now, when it comes to, if you're not interested in using the CPU pull mode operation, there's also interrupts. Interrupts by default are when a packet arrives at a ring, hits the queue, that queue will then call an API or a network API to actually hit the host CPU and say, hey, there's work to be done here. And it'll actually operate and process that packet. Now, interrupts happen in real time as packets are received. So one of the things you can do is use interrupt moderations, which will allow you to reduce the frequencies and set it at a default of 20 to 64 microseconds TX versus RX. This will reduce the frequency of the interrupts, but it can have some other consequences. If you're constantly receiving packets, it'll actually slow down the processing in this case. So that's why there's a capability that we support called dynamic interrupt moderation, which aims to strike a balance between latency and when you're receiving a lot of packets, actually increasing your interrupts. But when you're not receiving a ton of packets, it's not going to operate in a high interrupt mode such that you're actually going to reduce your CPU utilization in that case. So interrupts come from the queue, and we also want to talk about a couple other things when it comes to queue management. So by default, all of our instances support receive-side scaling or RSS. But there are certain cases where you may want to use a single queue and a single host CPU to do your network I/O or your network operations. In this case, all of your packets will be received on a single queue and then be processed on the single host CPU. Now, with RSS, which is enabled by default, it'll actually distribute that and it'll use a hash. So Scott mentioned it earlier, I believe, the CRC32 or the Toplitz hash, which allows you to distribute flows from all of your different queues and then to up to the number of queues that are available on your host CPU or to the number of CPUs available. Now you can also, starting with Nitro v3, evaluate and manipulate that hash such that you can define and distribute where those packets will actually land so that you can use specific queues for specific workload applications. Now, in addition to RSS, we have a capability called RPS, or Receive Packet Steering. Receive Packet Steering is a kernel operation that actually allows you to further distribute your packets across your host CPUs. In the left-hand example, what we were using was RSS, so we're using up to 8 queues. We're distributing across 8 host CPUs. But then you have the other 8 CPUs doing maybe business logic or maybe not. In this case, with RPS, what you can do is distribute packets from the 8 CPUs processing packets and distribute them to the other 8 CPUs so you can distribute your load more effectively. And then another capability actually we recently launched within the last couple months is called ENA flow steering or N-tuple filtering. So let's say and this is only available on Nitro v5. So in this slide, I've actually updated it to a C8G 8x large instance with RPS, but also now with flow steering. In this case, let's say you're receiving a packet to port 22, you're receiving a generic TCP packet and a generic UDP packet. Now those will use your hash depending on whether you configure one or not, CRC32 again, or the Toplitz hash, and they'll be hashed to each one of their respective queues based on that hash. However, let's say you want to define your SSH traffic to port 22 to a specific queue, your TCP traffic to another queue, and your UDP traffic to another queue. In this case, within ETH tool, you can configure your flow type, TCP4, destination port 22, and then actually index it on your Q0 such that all of your port 22 traffic will hit Q1. You can do the same thing for TCP traffic such that it'll hit port or Q2 or Q1, Q2, and then UDP traffic for the following queue. This will allow you to distribute your load in a more 5-tuple based perspective, and you can use any number of filters there. So a single N-tuple, 2 tuples, all the way up to 5. So you can be very prescriptive in terms of where you want your actual traffic to flow in terms of which CPU or which queue, and then ultimately which CPU. Now you're limited, or you have the capability up to the number of CPUs on your host. So in this case, you have 16 CPUs on the instance. Therefore, you're allowed up to 16 individual rules to distribute that traffic. And now we've touched on monitoring a little bit throughout this presentation. We have our bandwidth in and out allowance exceeded, PPS allowance exceeded, but we also have something for contract allowance exceeded and contract allowance available. There's also a metric for link local allowance. We're not going to touch on that here today, but really from this perspective, we haven't touched on the contract allowance exceeded and available, so we want to dive into that a little bit more. But first, just want to highlight that these are all available natively within ETH tool, but you can also use the CloudWatch agent to export it and use them in the CloudWatch such that you can alert and monitor scale against these metrics. So I touched on contracts briefly earlier. Contracts are used to track state of your various flows hitting your EC2 instance. So within the Nitro firmware, we're actually counting and indexing the number of connections each EC2 instance has, and then within your ENA driver, we're actually tracking that and exporting that as a metric. So we have the contract allowance available, which tells you how many available connections are still left, and then how many, or if you've actually exceeded that available will go to 0, and your available, your available will go to 0, and your exceeded will start to index up as you're starting to lose connections. Now, that becomes a real problem, particularly if you're exhausting connections and you don't know what to do. In this case, one of the things we launched about a year and a half ago was configurable idle timeouts, such that you can take your TCP configurable idle timeout from 5 days, which is the current default, down to as low as 60 seconds. So if a connection times out, we're not seeing any additional packets, and you configure that at 60 seconds, that connection will then be expired, and then we'll free up that resource or that memory so you can establish a new connection. Likewise, from TCP, we also support that on UDP in a single stream in a bidirectional manner, such that you can adjust that configuration on the UDP bidirectional case from 180 seconds down to 60 seconds. Now, contracts are just a memory. It's state mapping inside of Nitro. And another thing that is memory is a network address unit. So Scott mentioned this earlier when we're actually establishing a connection. We have to look up the remote interface. And to do this, your Nitro card will actually call the mapping service when it's trying to talk to a new instance, and it'll look up the location of each one of those instances. Now, inside of your VPC, you have all the instances you're talking to, but you might have hundreds of thousands of instances you're not actually talking to. In this case, we'll look up the individual location of your instances you're talking to, but we won't actually look and load the location of your instances you're not talking to. This allows us to optimize memory, but then it also allows us to scale your VPCs to sizes that I believe are unprecedented in the cloud. Today, we support 128 network address units inside of a VPC by default, and you can double that up to 256. With a pure VPC, we support 256,000 network address units by default, and that can scale up to 512 network address units. And that concludes the monitoring section. So here,
Thanks, John. So what we've taken you through a journey here today is starting at the application layers, things that you can do at the application layer, how you assign processes to specific CPUs to isolate their workload from any interrupts from the network. We've then taken you down into flow controls, where you can use the kernel to manage the queue structures and transmits. Then we've taken you into drivers, where the different drivers for the ENA are relevant, and we've taken you into the flow state of what's happening in Nitro. So with that, we want to give you an action plan. This is what we hope you walk out of here with and says, okay, guys, this is what we're going to do. First, know your traffic types. Know if you have any whale flows. That would be IPsec or GRE or other types of tunnels. Know if you have TCP or UDP flow entropy. Identify if you have sufficient entropy in your flows, and whether you have single flows that are hot or whether you have many flows. Now, once you have your traffic types, then you can build a traffic profile for each of those traffic types. This is packets per second, bits per second, and connections per second. And with that traffic profile, now you'll start to understand if you're going to run into any kind of constraints with your traffic moving across Nitro. Now that you have your traffic profile types, now you can pick your instance. And with this, you'll be looking at the baseline in the burst specifications. Then you'll be looking at the Nitro performance. You want to test again to identify how many packets per second you're going to be able to achieve, and then how many interfaces that we're going to have. Note that the security groups are going to can be associated with those interfaces, and so you'll have different properties for those interfaces. And finally, you want to tune and monitor your instances. This is driver tuning, as John mentioned, getting the right drivers. ETH tool metrics, where you can get CloudWatch agent into your instance and get more specific, more detailed metrics, and you can actually get VPC metrics from CloudWatch as well. So this is your action plan for optimizing Nitro. Hopefully you can take this with you back and you can have an action plan for dealing with this. I'll turn it back over to John to close us out.
Yeah, thanks, Scott. So here, what you'll see is a lot of the QR codes or the nuggets we left throughout, so I'll give you guys a moment, and I can come back to this. But here we have our Nitro tuning guide. We talked a lot about different generations of Nitro. We have an actual user guide that maps your EC2 instance to a Nitro generation. Talked a lot about ENA best practices or driver best practices, so you have that. Talked a lot about connection tracking and on-track connections, so a link to user guides there, as well as network address units. And then a couple other capabilities here from CloudWatch, ENA Express, how to troubleshoot and manage microbursts, and then finally our various networking specs for burst and baseline bandwidth. And of course, it's day one it's always day one at AWS first. But it's also day one of reInvent, so I want to highlight a couple additional sessions. We have a couple distinguished engineers, VPs, who will be talking about some of the latest things we're doing in the compute track, or in the compute space, as well as the networking space. We have an advanced design and what's new within networking, NET402. So a couple of our colleagues will go into all the latest and greatest capabilities we've launched in the last year there. We have application networking, NET317, as well as a couple additional compute tracks to look at various additional Nitro capabilities, but also additional generations of Graviton instances that we recently launched. So with that, I want to thank you guys all for your time, and please ask you to complete the survey. Thank you.